Hey guys, this is Professor Janacek, and I want to talk to you about curl of a vector field. Again, I want to remind you of the del operator. That is the partial derivative of the first component with respect to x, the partial derivative of the second component with respect to y, and the partial derivative of the third component with respect to z, and that is written as a vector. All right, so what is curl? Well, for f being a vector field, the curl of f is the cross product of the del operator with our vector field f. Now, before we talk about how we calculate this, let's talk about what is curl. Well, curl measures the rotation or the spin of a vector field at each point. So at each point, what is the rotation or what is the spin in that vector field? If we are looking in a two-dimensional situation, then our vector field f could look like the vector field fg. So it has components f and g. And the curl of f, again, it's the cross product of the del operator with f. So that would look something like the partial with respect to x, the partial with respect to y. We're only in two dimensions here. And then f and g. We're going to take the determinant of that matrix. Well, what does that look like? Remember, that is the partial with respect to x of g minus the partial with respect to y of f. In three dimensions, it can be a little more challenging. Let's let f be the vector field fgh. Then what does the curl of f look like? Well, in this case, I've got my I, j, and k unit vectors, and then we've got the partial with respect to x, the partial with respect to y, and then the partial with respect to z. And then finally f, g, and h. We're going to take the determinant of that matrix. Just as a review, what does that look like? Well, let's see. Remember, the way to do this is I get rid of those first two and just look at the remaining bit and work it just as the two-dimensional bit as we saw a moment ago. So that would give us the partial with respect to y of h minus the partial with respect to z of g. That's the I component. Actually, let me move this down a bit, make sure I have room here. Oops. I can get this to work. Well, hopefully I've got space under there. Okay. And then remember for the for computing this cross product, the next one is subtraction. And now we're going to kind of imagine getting rid of the row and column that has j, and then what's remaining we're going to consider as the two dimensions just above. So that would be the partial with respect to x of h minus the partial with respect to z of f. Again, notice I'm working only with these two portions. By the way, at this point, a lot of times people will take this negative and distribute, in which case you could then turn those around, and that subtraction would actually, in a sense, commute. And this is the j component, and then finally we will add the k component. We will get rid of the row and column that has k, looking just at that 4x4 matrix that's remaining. Find that. If you find the cross product of that, which is, what is that going to be? The partial with respect to x of g minus the partial with respect to y of f, and that is our k component. Oh my goodness, have to remember how to do cross products. But there we go. That is curl for a three-dimensional vector field. Now, a couple things to make note of. If the curl of a vector field f is equal to 0, notice that's a 0 vector, then we can say that the vector field is irrotational, which makes sense. Remember, curl is telling us the rotation of it. It's 0. That means it is irrotational. Another thing to make note of is that if we have an irrotational vector field, on a simply connected region, and this is, we'll look at this in R2 space, we say that these are conservative. So that's how we define a vector field as being conservative. Now let's take a look at an example. Let's compute the curl of, oh, there it is, three-dimensional vector field. First thing I think we should do is go ahead and identify what are the functions. F of x, y, z is just 0. G of x, y, z is our second component there, which is z squared minus y squared. And then finally, let h of x, y, z be that last one, which is negative yz, that third component. I also want to go ahead and start looking at the partial derivatives. So the partial derivative of f with respect to y is 0, and the partial derivative of f with respect to z is also 0. Notice it's the partial derivative of f with respect to y and z. For g, look at the partial derivative of g with respect to x and with respect to z. Partial derivative of g with respect to x, notice there are no g's in there, no x's in there, so that's 0. The partial derivative of g with respect to z is simply 2z. The y portion of that becomes 0. For h, we'll look at the partial derivatives with respect to x and with respect to y, but not z. Partial derivative of h with respect to x, there are no x's in there, so that's going to give us 0. And the partial derivative with respect to y is simply negative z. All right, so now we're ready to dive into the curl of f. I'm just going to follow this idea right here, computing each one of those. Let's just write this down for good measure. That's the partial of h with respect to y minus the partial of g with respect to z for the I component. I'm going to go ahead now and distribute this negative and commute those. So that's going to give us plus the partial of f with respect to z minus the partial of h with respect to x. Again, notice what I did there. Again, oops, distributing that negative and commuting those. That is our j component plus the h component, the partial of g with respect to x minus the partial of f with respect to y. That's for k. All right, so what do we have? putting this all together, just kind of matching what we've got. Negative z minus 2z for the I component plus 0 minus 0 for the j component plus, again, 0 minus 0 for the k component, which gives us simply negative 3z for the I component. Don't forget, you could write this as negative 3z, comma 0, comma 0. And there is the curl of f. Enjoy!